Okay, everyone, my name is Takuntang Phati. Today I'm going to teach you about the gas and breathing. So, uh, even if this is the second time I didn't have the chance to see you guys in person, unfortunately for the heavy rain right now that we have suffered, so we might have to learn this via the online way. I hope that you would find this video to study and learn. And so please enjoy about this. And I will try my best to let everyone in this class to understand. And don't forget to uh, do the quiz, okay? Because that is the way you get the score for the formative assessment. And that would be the hint to the final exam as well. Okay. If you need anything, just ask me, okay? Okay. Right now, I'm going to share my screen. Okay, great. Shoop, 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 shoop. Let me see that uh, it is recorded. Okay. And right now, gas. Okay. This is the lesson for today, okay? Gas and breathing. Uh, the objectives for this class is to understand the standard laws of gas and its properties. And another one is to learn how to describe the mechanism of breathing and the relevant technology in medicine. Okay. So, what is gas? What is the nature of gas? Gas is a type of fluid, but but the distance between each molecule is far from the case of liquid state. So when you add the gas into the container, it will spread all the way to cover all empty space or space. Okay, so for the gas, it is much more compressible because you can press it, you can pull it via container. Okay, no matter how much container size is, you can add the gas and it will spread to cover all over inside it. Okay. Uh, Under the similar condition, for example, pressure and temperature, the gas will follow with the same law, which you can see for the following contents. And we also apply the ideal gas for the simplest case, which each molecule of the gas has no interaction, which means that they can collide to each other. They can collide. They can crash to each other, but they cannot have the potential between each other. Okay. So for the first law, it is Boyle law. So Boyle law state that the pressure of the gas is inversely proportional to the volume of gas. Okay, uh, I will give you more explanation about this. Okay, I would like to make sure that you guys get uh, this thing on the same page. Okay, just imagine. Okay, just imagine that you have the container. In this case, it's like, sorry, it's too small. Okay, right here. And you have gas spread all around here. Okay, you have gas inside. this container. Okay. If you try to press it, for example, you try to decrease its volume. You try to decrease its volume. With the same amount of the gas inside, each gas will have less space, right? So right here, when they have less distance between each other, they collide more to each other, and then makes it collide more on the container. They collide more frequently than usual, which it makes the pressure goes higher. So right here, for example, we have volume 1, and right here we have volume 2. So as you can see that V1 is larger than V2. And for the pressure 1 must be less than the pressure 2 because the distance between each other is reduced. So they can press, they can collide to the surface more frequently. Just it. That is why we would have this relation that the pressure is inversely proportional to the volume of the gas. And that is the first law. For the next one, Charles' law. Charles' laws at the constant pressure because they fix pressure, right? Okay. The volume of the gas is directly proportional to the temperature. So this one is like solid. Okay. For example, for this case, if the pressure is constant, so we fix pressure, and we have the container, for example, in a box right here. We have a box like here, and there is a piston. Just assume that right here is a chamber that contain gas. With volume V1 at temperature 1, and then you guys heat it up. Right here. Then you heat it up. For example, you just put fire on it. Sorry. You burn it outside, not inside. Okay. When you try to burn it, the temperature T2 must be larger than T1 because you put a lot of heat into the system. And then the piston right here. Oh, sorry. The piston right here would be moved. Okay. From here. Move to here. Okay. This because the gas inside this with high temperature, they will get higher energy. The high energy, so they push all the way that they can. In this case, the wall can be moved. So the volume for this case should be increased. And they find that the change of the volume and temperature is proportionally. Okay, so you can write the relation of V and T into V equal to KT, as well as for this one, P can be written in this term, P equal to K by V, where K right here is a constant. And K right here is a constant as well. Okay. And for the next one, the last one is the Gay-Lussac law. When you keep the volume of the gas or the container constant, the pressure is directly proportional to the temperature. For this case, if you have the container, I would fix in a box right here, and there is gas inside it. When you burn something, you add energy into it. So they have more energy, so more activity. Then they hit the container or the chamber more frequently, higher and higher, to, to build up the pressure. That is why the pressure is proportionally to temperature. And we can write the equation as P equal to KT. Before I go next, so to put everything on the same page right here, we from the boiler, we have pressure equal to K by V. And by Charles' law, we have the volume equal to KT. And for the last one, from Gay-Lussac law, the pressure equal to KT. So I always ask students that, can you see that? We have the to our equations. The question is, are these cases the same thing? Are these cases the same thing? The answer to this one is no. K in each equation are not the same. So to play safe, I would like to call it K1, K2, and K3. Okay. So because we have this relation, so we can combine each other. We can combine each other. For example, we know that P is inverse proportional to V, right? So we can write it PV equal to K1 like this. And we have V by T equal to K2, right? And we have the ratio P by T equal to K3. So because on the right hand side of the equation is already constant, so we can put the relation of each quantities together. You can combine because here equal to K K4. For example, in the case that you fix temperature, right? You fix temperature PV equal to K4T when you fix temperature. Right here will be equal to K1, right? And in the case that you fix pressure, so V by T equals to K4 by P, which is K2, right? Because right now you fix pressure. And for the last one, you can fix the volume. So P by T so equal to K4 by V, which is exactly K3 right here. Fix volume. So right now, by the empirical, this K4 equal to N times R, right? N times R. So N is the number of molecules and R equal to 8.314 joules per mole Kelvin. So as you can see right here, right? This NR is K4 that I already written, right? That I already wrote for you guys. Mhm. And here is the ideal law, ideal gas law, sorry. And here is the ideal gas law, where the pressure and volume multiplication equal to nRT. So N is the number of mole in the unit of mole. Okay. R is a constant. Okay. And right now for the Dalton law, uh, you can calculate the total pressure of the gas into your system by calculating from the partial pressure or vice versa. You can find the partial pressure of each gas in the gas mixture, right? Gas wells. For example, the total pressure right here is the uh, which is equal to nRT by V from the ideal gas. And the pressure of the total can be calculated from each type of gas. P1 plus P2 plus PT, blah, 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 until Pn. So, sorry, Pm. It depends on how many types of gas inside uh, the chamber. And in this case, there are M types here, M types. So uh, we can apply this to calculate the partial pressure because P in each term is called partial pressure, which means P1 is the partial pressure of the first type of gas. And here, if we know exactly the ratio of the mole of the first type, you can find the partial pressure of the first one, and so on. P1, P2, P3 until Pm. Okay. And air that we use to breathe is a gas mixture because there is around 79% of nitrogen. Then from uh, the last class that at the atmosphere, E at the atmosphere is 1 atm, right? And it can be converted into 760 torr. If you want to know that inside the air there is nitrogen around 79%, you would like to know that how much pressure from the nitrogen is. So you can use this fraction because you know that it is 79%, right? So it would be 79% of the total pressure, and it is around 600 torr for just only for the uh, nitrogen. And when you travel by plane, you go to at very high altitude. There is the pressure modulation, the pressure modulator inside the plane. That is the reason why we can breathe normally. However, there might be some incidents that the pressure inside uh, the plane would not be normal. There will be a mass right here shown in the picture that drop in front of your face. So you can use the mask to breathe uh, the the air with the normal pressure. And at the high altitude, as you can guess that the amount of the oxygen reduced, right? Which means that the partial pressure of the oxygen reduced as well. And for the case that if the partial here, partial pressure of oxygen, not the total pressure, okay? Just partial. Partial pressure of oxygen is less than total. We cannot breathe normally. And this incident might happen because it compensates the oxygen that is very low level. Okay. And before I go next, I would like to introduce the first law of thermodynamics. It's very easy for start because it contains just only 3 terms. The first one is heat, Q, right here, heat transfer to the system. In the thermodynamic system, there is 2 things. The system that you are interested right here, the system, and the environment. The way that system can communicate to the environment is from the heat. Okay. In this case, if I assume that the heat from environment comes in to the system, so the heat is a positive because uh, it flow from the environment to the system. Okay, right here, Q is positive, and the system will try to find a way to convert the heat from the outside to something else. In thermodynamics, there is two ways to convert. The first option is to convert heat into for the system. And work of the system is defined by pressure multiply the volume change, which means uh, the heat outside can be changed to the higher volume in the system, right? So when Q is larger than zero, it's positive. So the first thing that they can do is to increase volume of system. Here is the first it is the first way to convert the heat energy. The second one, the second way is to increase the internal energy. Internal energy. So this means that the temperature increase. Okay. So by uh, translation translation from for the interpretation for this one is that the heat when it go inside the system it can be changed into two things. The first thing is about volume. It's about volume. And the second thing is about temperature. That's it. Okay? Two things. Volume or temperature that can be changed from the heat outside. On the other way as well, if the heat is less than zero, which means that uh, the energy from the system is go is going outside to the environment. So the volume might be reduced, or maybe the temperature might be reduced. Okay. And here, for the effect of the gas pressure in diving, and you go diving, okay? Approximately, the gauge pressure would be increased by 1 atm for every 10 meters depth of water. For example, okay, for example, if you guys love to dive, right here, shoop, you dive underwater. For example, 10 meter. If you can see, if you can see from the picture and you remind the last time that I lecture, gauge pressure is rho g h. And if you remember, the unit is 1,000 kilogram per cubic meter, and g is around 10 meters square, and h right here is 10 meters. It is equal 10 to 5 kilogram per meter 6 square. Or in this case, you can convert this unit to Newton per meter square. Okay. Um, you can convert this. And if you consider P at the atmosphere is around 10 to 5 Newton per square meter. So this means that every 10 meter depth under the surface, the pressure increase 1 atm. For example, in this case, the pressure at the surface is around 1 atm, right? But you have to add the total pressure at 10 meters equal to pressure of the ATM plus P gauge. So it would be 10 to 5 plus 10 to 5 Newton per square meter, and it equal to 10 to 5 right here. It's 10 meters. Just imagine that if you are in the depth around 100 meters, it would be equal P ATM plus P gauge. But because you already know that the P gauge will increase 1 atm every 10 meters. So in this case, you have right here. And the answer is 1.1, 10 to 6 Newton per meter square. The common mistake for you guys is that you always forget this one, right? If you forget this one, the total pressure would be less than it should be. Okay, so don't forget to add the P at the ATM. Okay, and next, uh, this is important for you. The partial pressure of the oxygen more than 2 atm. It will lead to shock and coma. Okay, to just only 2 atm of partial pressure, not total pressure. Okay, just 2. And another one is also lethal as well, because if the partial pressure of nitrogen is more than 2 atm, it would lead to the lethal situation, which we always would like to avoid. So if you see here, you can see that uh, at the risk level of partial pressure for the oxygen, P of O2 larger than 2 atm is dangerous, and P of nitrogen larger than 2 atm is dangerous. So which one is more dangerous? Can you guess it? Which is more dangerous? Because they set the level at 2 atm. If higher than this, it causes lethal. Okay, before you can answer about this, you have to understand about right here. For example, here is air. There is around 78 or 79% of nitrogen. And for the oxygen, it's around 25%. No. 20, around 18%, right? So Just imagine that if you go to underwater with higher and higher pressure, P at ATM equal to 1 ATM, right? And the partial of oxygen would be around 1.18 ATM. However, for nitrogen, it's around 0.79 ATM. When you go deeper and deeper, the nitrogen, the partial pressure of nitrogen would touch 2 ATM before the oxygen. That is why when you go scuba diving, they have to concern, you have to concern about not just only the content of the oxygen inside the tank, but also the pressure of nitrogen, because this will reach 2 ATM before oxygen. Okay, nitrogen reach 2 ATM before O2. That is what you have to be careful. Okay. So in some case, in the scuba diving, they try to avoid this to happen by uh, contain only heat and oxygen in the tank to avoid the higher amount of nitrogen at really low level under the surface of the water. So to fix this, get rid of nitrogen. Okay. And here, to describe about the relation of the dissolvent of the gas, we use the Henry law that the gas can dissolve in liquid. The concentration of the gas that is dissolved in liquid is directly proportional to the partial of the pressure of gas. Okay, and the dynamic equilibrium is reached when the number of gas molecules enter and leave the liquid. Okay, guys. To explain this more uh, with more good explanation, what I would like to say to you is to just imagine a chamber right here. Okay, if there is some liquid here and gas over the surface of liquid right here, gas here and liquid here. So if you add pressure to this system, if you add pressure, no matter how uh, no matter method you add, okay, but you find a way to add the pressure. So the gas will move all the way, push each other, and as well push to the surface as well. So higher pressure of gas. This would lead to higher, more frequently collision of gas to the surface of liquid. So this would lead to good dissolve because gas bombard on the liquid and they can dissolve into liquid more efficiently. That's it. And we would call it dynamic equilibrium because uh, if the rate if the rate of gas dissolve into the liquid equal the rate of gas convert to sorry if the rate of incoming rate of incoming and here is the rate of outgoing. If these two rates are equal, it would be the dynamical equilibrium. Okay. So the effect of dissolved gas in diving. For the scuba diving, if the pressure is such large that gas is additional dissolved into the bloodstream. For example, when you dive under water at very low altitude, very low altitude, some gas, for example, nitrogen, could dissolve into your bloodstream. Okay, and if you go to the surface immediately, those gas will leave your blood and will leave the air inside the bloodstream, which is very dangerous situation because this uh, this bubble that happen from the gas that leave your blood would make some block, so the blood could not run or send the oxygen or maybe carry out the carbon dioxide from some space. And just imagine if that happened in your brain. So your brain might lack of food and there might some high amount of carbon dioxide that cannot be released from your body. It might cause the death of the cells. Then, if you dive under the water at very low altitude, just slowly go to the surface because we would like to avoid the gas rapidly leaving your body. Okay. And here is about the kinetic energy of the gas. We talk about the gas movement. We talk a lot about it, but we never calculate it. We have the relation from the ideal gas right here. And from the empirical and um, theory and empirical way, we would find the relation of pressure on the gas would be proportion to the first thing is the number of the molecules, right? Mass of that molecules, right? But inversely proportional to the which we already know. Okay, and another one is about the average of the square of speed, not just the speed, but just the average. Uh, average of the square of speed here. Okay. So why would we call average? Because when we consider gas, we don't consider just only one atom or one molecule. We consider it like a mole. So we have to find uh, the velocity square of each one, and then divide that, and then divide by the number of total molecules. So you may see that it is impossible to find this value because there is almost infinity number. However, we can use the statistic to find the average of this value, not by measure each one by one. No, we don't do that. We can use the uh, statistics of the molecules. Okay, when you combine relation, you get this relation. Okay, as you can see. So right now, you can see that the average of the velocity square would be proportional to temperature. Because in the system, you can fix the number of the particle, right? And the mass of each molecule is fixed. So n right here is proportional to the n, so it is fixed and r is fixed. So right now, we can find that v right here is proportional to the temperature. Okay. And here is the relation between the speed and temperature in the full form. Okay. And right here, you can see that this is the kinetic energy. And the number 3 right here has the significant meaning because 3 right here is the number of degree of freedom. In this case, you can call it 3-dimension because gas has the way to go. For example, X, Y, and Z. Okay, 3 dimensions. That is why it would be 3 right here. And you can find the VMS, which is the root mean square, because we prefer the unit with suppose n per second, or maybe centimeter per second, or maybe kilometer per hour, right? Here is the unit of VIMS, which is better than V square, because V square it is m square by second square or centimeter square by second square. We are not used to this unit, but the unit right here is more practical for us to understand. And here is the velocity distribution. As you can see that for higher temperature right here, Normally, gas would distribute their velocity, right? But the the most molecule would have the velocity. Okay. You can see that this relative probability is proportional to number. Okay, so you can see that at t equal to 1100 Kelvin, the velocity is 750 meters per second. Why? T2 at 300 Kelvin has the velocity just around 300, oh sorry, 400 meters per second, right? So it's like the relation that V would proportional to square root of the temperature. Mhm. So the most the most amount of the gas right here should be represent the majority of the gas behavior. So to apply to the anatomy of the respiration system, uh, the protagonist for you guys that can uh, inhale and exhale is diaphragm, because the diaphragm uh, right now, if the diaphragm go lower, the volume inside the lung would be increased. Increase volume, right? This is inhale. And when the diaphragm move upper, it decrease volume, and that is exhale. Okay. So during the respiration of human body, the amount of gas would be different. For the nitrogen, by average, it doesn't change a lot. Okay. And I would call it the amount of nitrogen for the inhale and exhale processes would be insignificant change. However, oxygen and carbon dioxide. So as you can see that when you inhale, around almost 21% of the oxygen would be inhaled, right? But the outside, the exhales, it release the oxygen around 16.3%. However, for the carbon dioxide, for the inhale, only just almost 0% in our environment. However, the body would produce a lot of carbon dioxide and try to release it around 4.5%. So just just roughly speaking that uh, we O2 into our body around 4%, right? And we have carbon dioxide around 4% go out. Oxygen is lighter than carbon dioxide, which means that the more you breathe, the less weight you got. So you get thinner and thinner if you breathe. Try to breathe and you will you get thinner and thinner. Okay. In this case, it's about the lung capacity. So you could see that if you breathe normally, the volume of the lung would change from 2.7 and between 2.2 and 2.7, just it. But if you inhale it deeply, if you breathe deeply, the maximum inspiratory level, I mean the the higher volume of the lung possible is around 6 liter. Yeah, right here, right here, right here. And when you try to breathe out, try to breathe out as much as you can. Your lung capacity, your lung capacity would not go to zero, but it's stuck around 1.2 liters. So the body of okay, the nature the nature of our body try to keep at least 1.2 liters in our lung. Why? Why? Why not go to zero? Because it would release all carbon dioxide and you can breathe in oxygen. Why just leave it just only 1.2 liters, not 0 liters? Why? The reason is here. It's about the gas exchange. You cannot leave your lung into zero capacity because right here, the subunit here, alveoli right here, it needs air because it's like a bubble. It's like a bubble. It needs air right to fill in here. If there is no air, there will be no way that it can pop out. Okay, it will be flat. And when it is flat, the efficiency to absorb oxygen and the efficiency to release carbon dioxide would be abruptly decreased. So we need to hold the volume of alveoli to hold this form to maintain the efficiency of the gas exchange. Because when it collapses, it will not be returned to the stable state anymore. Okay. And the rest, you can read the rest as your bedtime story. Okay. And one application of uh, gas and breathing is the heart lung machine. So you can bypass the operation of breathing. For example, when you have to bypass uh, the direction of the blood because there is the heart surgery. You might have to move your blood into the heart lung machine instead of heart because you put not do to do the surgery and the blood came out. So they have to suck out all of the blood. Okay, right. And right here there is the mimic machine that pretend to be the lung. And then move it to the heart. In this case, uh, it is used during the surgery of lung, not heart. Sorry, when you would like to change your lung or anything, you need some machine release the carbon dioxide and absorb the oxygen to the body. So the machine just pretend to be your lung. And here just the end for today's class. And the next section will be the active learning section to solve some problems which are necessary for you guys, not just in the exam, but it would be some necessary skills for you guys in the higher education. Okay, I would like to stop this video here, and I will start the video about solving the problems